Okay, so the last talk will be online with Wolfgang, who will talk to us about CertiCoq-Wasm.
Yeah, welcome everybody. Thanks for joining the presentation of our project, CertiCoq-Wasm. So in one slide, our project is about compiling Coq code to WebAssembly in a verified way. So imagine you have developed a program in the Coq proof assistant. That is, you wrote a program in its Gallina language and proved that it adheres to some specification. Now you want to integrate that into a real-world application that may be written in a language like C or OCaml. So what you want to do is you want to extract your Gallina code to such a language. Now, Coq comes with an extraction to OCaml, and other projects target other languages, including C. But in this project, instead of languages like that, we want to target WebAssembly. And what this will allow you to do is that you can run your Coq programs on the web. And that is because modern web browsers like Chrome or Firefox come with a runtime for WebAssembly programs to accompany JavaScript programs. Now, while WebAssembly is gaining popularity in other use cases as well, if you're not yet familiar with WebAssembly, a good way to think about our project is that it allows you to run Coq programs on the web. And then as a second point, our transformation is verified because if you took all this time and effort to verify your Coq program, you don't want that the extraction mechanism introduces a bug. So given that the extraction mechanism is verified, you can be quite certain that the produced program does what you originally, that it does behave in the same way as the original program, right? As part of this presentation, I would like to convince you that our tool is practical and useful in practice. So we built a little demo application where we built a little website that allows you to compute the SHA-256 sum of an arbitrary input string. So we took an implementation of SHA-256 that's developed and proven correct in Coq and extracted it using our tool CertiCoq-Wasm to a WebAssembly binary. And then we wrote a little bit of JavaScript to write this little user interface around it. And then you can input a string, and our CertiCoq-Wasm tool produces the same result as the standard browser API. So in the remaining presentation, I'll talk about how it works, how it compares to other ways of extracting to WebAssembly, and then we have another practical application. I'll start with an introduction to WebAssembly in case you're not familiar with WebAssembly. So, as I've already mentioned, it's supported by the major web browsers. And this is cool because you can now use your favorite programming language to develop web applications. But also outside the web browser, there's WebAssembly is gaining a lot of traction, in particular in blockchain applications, in edge computing, but there are really many other applications, and people are really excited about it. And the reason people are getting excited about it is because the WebAssembly specification defines a secure sandbox that has fairly simple and clear semantics. And you also, in addition to the security property, you also get binaries that run fast. And in our case, WebAssembly, what's useful for our purposes is the WebAssembly mechanization. There exists one in Isabelle and Coq, and our work is developed in the Coq proof assistant. So we depend on this WasmCert project. WebAssembly programs are organized around modules. So this is a very simple example module that has two entities. So there's a global variable that's initialized with 41, and then there's a function that adds 1 to this global. And given that WebAssembly has the sandbox property, only the exported add function is visible to the runtime, but the global, for example, is not visible. You would have to mark it as exported explicitly. A word on the a word on WebAssembly's operational semantics. So the host runtime has its own state, but since the binaries regenerate do not interact with the host runtime, that stays the same, so we omit it. And what's of most interest to us is the store and the frame. And these two capture the state of the machine during execution. So the store captures the global state of the execution, mainly the current values of global variables and the current contents of the WebAssembly's linear memory. And then the frame contains, a function local stack frame contains the current values of the local variables. And then we have a set of instructions, list of instructions. So just to give you a sense of what it's like to step through a WebAssembly program, this is the program from just before, and you can see the configuration, the start configuration at the top. So initially there's the value 1 on the stack, and then as in the first step, the machine executes this global.get, which initially has the value 41. So the two values 1 and 41 on the stack, these are then added, and finally the global is updated with the new value, resulting in a new store S prime here. Now some background on CertiCoq and the lambda intermediate language. So as the name of our paper suggests, our work builds on CertiCoq, and in this figure I'm showing you a simplified version of the CertiCoq pipeline. So CertiCoq comes as a Coq plugin, so we start at the top with the original Gallina program. That is then reified into the Coq AST that is part of the MetaCoq project, and then follow various steps, various transformations with various intermediate languages that I summarize here as CertiCoq core. This includes some optimizations on the lambda level as well. And finally, CertiCoq generates C code from this final lambda language. Now, all of these steps are verified. For one or two of them, the verification is a work in progress, but once they're done, you get a compiler that has an end-to-end correctness statement. And instead of generating C code, we insert our backend here right after this lambda intermediate language and generate WebAssembly code from this intermediate language. So what does lambda look like? Lambda is an untyped lambda calculus in a normal form. I will start with the values. So in lambda there are three kinds of values. There's constructor values, there's function values, and there's primitive values. In our case, primitive values means 63-bit primitive integer values. And then you have various expression types. So you have constructors, you have projection to access constructor arguments, you have a case distinction, then you have function definitions and function calls, and then you have primitive values and operations. And these primitive values and operations correspond directly to the ones that are available in Coq itself. So in Coq, to enhance performance, you can use primitive integers and operations and floats, and I think also arrays. We currently only support primitive integers, and we support all the 24 operations on them. Think like arithmetic and logical operations. So this is what a typical lambda-nf program looks like. This is the program you get when you compile the Coq term length of the singleton list. It contains just 0. And what's notable here is that you get a top-level set of function definitions. And this set of function definitions is followed by the main expression. The fact that function definitions only occur at the top is ensured by a previous optimization on lambda-nf in the previous CertiCoq pipeline. And the fact that function definitions only occur at the top makes it easy because we can convert them one by one to a WebAssembly function in the final Wasm module. And the main expression, we translate that as well and place it in a main function in the final Wasm binary. So now I talk about how our backend works. So we have a top-level compilation function that takes a lambda-nf expression of the form that I've just shown you, and it produces a WebAssembly module. This module has a Wasm function for every lambda-nf function and a main function containing the main expression. And then it has various other entities, such as a linear memory, which is used to store constructor values and primitive values. And then we have a bunch of globals and other entities. Second, we have the cogen function, which takes lambda-nf expressions as well. And this is the function that actually produces Wasm code. So this will return a list of Wasm instructions, and these are placed in the Wasm functions as a function body. The Wasm binaries we generate use a simple memory model without garbage collection. So what happens is that whenever we allocate a value in the linear memory, we preserve a high level, a high watermark, so to speak, and this ensures that old values are never overwritten, but we just write a value to the next free space in this linear memory. And given that the Wasm linear memory is limited to 2 GB, if we need more, then we terminate with the out of mem flag set to 1. So there's a limit to the size of programs we can run. But as we'll see in the evaluation, this is not our set of benchmarks. This is not a limitation in practice. So how does this cogen function work? The main consideration here is how do we represent lambda-nf values in WebAssembly? And for that, we choose a representation that is quite similar to, or very similar to, the one used in CertiCoq-C backend, which in turn is essentially the same as the representation the OCaml compiler uses. So we represent lambda-nf values as I32 integers, And recall that there are three kinds of lambda f values. Function values are represented by the index of the corresponding function. Primitive values are boxed in the linear memory. And then we have constructor values. Non-linear constructors are also boxed in the linear memory. And that is essentially a pointer pointing to a segment holding the constructor tag, followed by the arguments. And then that is not necessary for non-linear constructors, which we can just identify by the tag. We shift it to the left, add 1, so we can distinguish the two constructor types. This brings me to the correctness statement we proved about our backend, and I'll just go through it. So we have a top level lambda NF expression that has some function definitions, and if you evaluate this expression in the empty environment, you get a value v. And finally, there's if you compile this lambda NF expression with our backend, CertiCoq-Wasm, you get a Wasm module. Now, given these, it holds that the module instantiates through an initial store and frame. Instantiation in WebAssembly context means transformation to the original runtime representation. And this only succeeds when the module is well typed. So this includes the proof that modules generated by CertiCoq-Wasm are well typed. And when you call the main function on this initial configuration, you're left with a final store SR prime that has which the global variable result has the correct value set. And this here is just the value relation I've shown you just before. Or as another option, we ran out of memory. That's also okay. The proof is a forward simulation over the evaluation derivation, and you're welcome to check the paper for the details. This is a visualization of the proof, and I'll just explain it on a very high level. So as before, we have the initial lambda NF expression that is evaluated on an empty environment to a value v. Lambda NF expression is compiled to a module, then it holds that it instantiates, and if you call the main function, you're left with this final store SR prime, for which the result variable is set correctly. And this is ensured by another relation that links the lambda NF environment to this pair of store and frame throughout the execution to ensure that whenever an evaluation step is taken on the left side, the same behavior is simulated on the Wasm side. This brings me to the evaluation. So we choose a set of benchmarks that include the CertiCoq benchmark suite. These are mostly some micro benchmarks, but also more complicated, computationally expensive benchmarks. And then we choose some of our own. So we choose the Ackermann function, we include the Ackermann function, and we include a benchmark Coq prime. And what's special about the last benchmark is that the Coq program uses Coq 63-bit primitive integers and operations. Since we're not aware of other extractions that directly target WebAssembly, we combine various extractions via intermediate languages. So we have an extraction via C, via Rust, via OCaml, and via malfunction. Malfunction is a wrap around one of the OCaml compiler's intermediate languages. And then we combine these extractions with off-the-shelf tools. So this is mscripten, which is a very popular tool to compile C-like languages to WebAssembly. This is just the Rust compiler, and we have this Wasm of OCaml tool. This is our work, and once the remaining stages are verified, this gives us the first extraction to WebAssembly that has an end-to-end correctness statement. Whereas the others, you have to trust these programs, and the two on the left, for example, include all of the LLVM infrastructure in the trusted computing base. Now, to be a little more precise, all of these extractions target different versions of WebAssembly. So Wasm 1.0 is the original standard as it was defined in 2019, but that standard has been evolving and was extended with multiple proposals. The one we target includes the tail call proposal. So in Wasm, you have to want a tail call. There's a specific instruction for that, which we make use of. And then there's a further proposal, the WasmGC proposal, which adds garbage collected reference types to WebAssembly. So you get heap allocated structs and arrays for which the runtime is responsible for garbage collection. Now you can see that these are not exactly perfect to compare, but that's what we've got. So this is the performance comparison of our tools. I'll start with the failure. So our tool is the only extraction that generates a Wasm binary that computes the correct result for all our benchmarks. And the other extractions either produce ill-typed code, like the first two here, or they don't support the Wasm, or they don't support the 63-bit primitive integer operations, as is the case with the Rust and the mel function extraction. So for these two, the compiler just refuses to compile the input program. And then the extraction via C produces a binary that crashes when you run it. Now, in terms of performance, we use all the other extractions in the production settings. So with all optimizations turned on, and then we have our tool without optimizations, and also with optimizations provided by the WasmOpt tool, which is a popular Wasm optimizer that's used a lot in the Wasm ecosystem. And then we have a prototype that also targets this WasmGC version, but that's an unverified prototype. So what you can see here is that compared to Rust or C, our CertiCoq-Wasm produces code that performs quite a bit better, that's faster. And compared to OCaml and mel function, we're roughly equal. So we're a little worse than the extraction via OCaml, and we're roughly equal to the one via mel function. But keep in mind that the OCaml mel function extractions target this other version of WebAssembly. Yeah, and then our prototype is quite a bit worse. In terms of the binary size, so above in the upper half, we have the ones that target Wasm 1.0. And for these, our tool generates the smallest binaries, except for the color benchmark, where the Rust one is better. But compared to the C1, we generate significantly smaller binaries. And the reason for that is that the C extraction includes a garbage collector written in C. that is verified and written in C. And from another perspective, you could say that well, with the extraction via C, you could run larger programs, but at the cost of having larger binaries. And for the ones that target WasmGC, we have, it depends on the concrete benchmark. So we are worse for some and better for some of the benchmarks. I skip to the conclusion. So we presented a verified Wasm backend for CertiCoq that significantly reduces the trusted computing base when extracting from Gallina to WebAssembly. We believe that it's fast enough and that the binaries are small enough for it to be practical, and we support the translation of primitive 63-bit integers and the operations on them, which most of the other extraction tools do not support. In the future, we also want to look at optimizations on the Wasm level, sort of Wasm-opt but verified. And if you're interested in that topic, please reach out to me. With that, I thank you for your attention, and I'll happily take some questions now.
Thanks. We still have time for 1 or 2 questions. Okay, I have a... Oh.
Hi, thanks for the talk. So in the malfunction setting, there is also a theorem about realizability semantics, the fact that we characterize the kind of, at which type we can guarantee a bit more about the function, just the execution, but also the interaction with the malfunction external world. Can you think about the kind of corresponding theorem in WebAssembly characterizing over which type of the function you can guarantee that the interaction with other WebAssembly codes can be safe? Does the question make sense for you?
I think you're referring to foreign function calls, is that right?
Yeah, for example.
Yeah, so there's a different project that adds a verified function interface to CertiCoq, and there's going to be a talk about this tomorrow, I think, called VeriFFI, and they present a verified foreign function interface, I think originally planned for CertiCoq C backend, but as far as I know, it should also be possible to make this work for WebAssembly. I've been told that it's generic and one should be able to make use of that.
Okay, thanks.
On slide 22, you showed the very poor performance with the garbage collector. Could you explain why this happens? Like it was in your prototype, I think, which you said.
You mean for the Coq Prime one?
Yes. What makes the garbage project, like what makes the version with the garbage collector so much worse? Do you know, or?
Yeah, so each 63-bit primitive integer is boxed in a struct, and in my opinion, this leads to a lot of memory accesses and storing values to the heap, because you have to always box and unbox these values, and because there are so many primitive operations, this happens quite a lot, and this does not happen with the other benchmarks. But I would like to say that this is sort of a prototype version, and I think it could be optimized if we spend some more time on it.
Okay, if there are no more questions, let's thank all 3 speakers again.